We've considered how to analyze most of the key elements of a language, but not all of them. A robust tool obviously has to handle them all. First, while assignments obviously transfer the taint from the source to the target, what should happen if the source is an expression rather than a variable? We must define the taint of operators. Usually, if an argument to an operator is tainted, then the expression containing that operator is too. So far, we have assumed we know which function a call will invoke. This is important for linking up the flow constraints at the caller with those in the callee. But what if we make a call through a function pointer? The pointer is not assigned until runtime, so that static compile time analysis cannot always be sure of its target. As it turns out, we can use a kind of flow analysis to determine the set of possible targets a function pointer could contain. The analysis follows the same principles of the flow analysis that we've already seen. This way, when analyzing a call site using a function pointer, we add constraints as if all possible targets were called rather than a single target. An even more coarse analysis of possible targets, for example based on a function's type, could also be used rather than one that more precisely determines the possible values of the function pointer. C-structs are records having several fields. The most precise analysis can track the taintedness of each field of a struct separately, as if they were separate variables. But such precision can be expensive. Alternatively, an analysis can track the taintedness of the same field of all instances of a struct, as if that field was a kind of global variable. Now this hurts precision, but is often a big boost to performance. An in-between position is to analyze only the taintedness of the struct as a whole, or to do so for only some of its fields. Note that these decisions are relevant to object-oriented languages. You can view objects as a struct containing function pointers, and so the trade-offs we've just considered apply in the analysis of object-oriented languages. Another way to aggregate data in a language is to store it in an array. And there are several similar trade-offs here. You can track taintedness of each element, or you could track it on the array as a whole. The challenge here is that while struct fields are constants, array indexes are computed by arithmetic. As such, it is sometimes hard to track them precisely at compile time because we won't know what arithmetic produces until we run the program. And so a hybrid approach is inevitably employed. Up until now, we have focused on how the analysis works. A key part of using it to perform security reviews is to properly label the tainted sources and untainted sinks. And there are many options here. We could label array indexes and format strings and SQL strings. We can also label functions that act as sanitizers or validators. These are library routines that take in tainted data and return untainted data. For example, a function that escapes an HTML string would be a sanitizer. Labeling sanitizers is needed to avoid false alarms. Finally, flow analysis need not only apply to finding improper use of tainted data, it can also be used to discover the improper disclosure of sensitive information. In particular, we can imagine labeling sensitive data as secret and untrusted output channels as public. And our goal is to prevent secret sources from reaching public sinks. In essence, this is the dual of the tainting problem, where the only difference is that the lattice and flow relationships are inverted. Finally, we should point out that flow analysis is not the only kind of static analysis, and in fact there are many other kinds. One common analysis that is often used to assist other analysis problems is called pointer analysis, with a common flavor of it called points-to analysis. This analysis determines whether two pointers are possibly aliases, that is, whether they could both point to the same memory. Earlier, we saw that knowing this is important for not missing bugs. In fact, Our tainted flow analysis involved a very coarse-grained form of pointer analysis within it. But more sophisticated analyses would improve precision. Significant advances have aided both the precision and scalability of pointer analysis in recent years. Another kind of analysis is called data flow analysis, and it was developed in the 1970s as part of research on optimizing compilers. Like the flow analysis we have already considered, data flow analysis focuses on the flow of values through variables in a program, but it maintains information about this flow a bit differently. One common data flow analysis is called liveness analysis, and it determines which variables at a given program point are still alive, that is, whether their values could still be read in the future. Other variables are dead, meaning that their values will be overwritten. Liveness analysis is an important part of allocating variables to machine registers during compilation. Registers storing dead variables can be reused. Data flow analysis techniques are also useful for security questions, and many industrial tools use them. For example, they can also answer the tainted flow question. Finally, another significant kind of analysis is called abstract interpretation. It was invented in part to provide a theoretical explanation of data flow analysis, but it has grown into a style of analysis in its own right. The key idea of abstract interpretation is that a static analysis is an abstraction of all possible concrete runs of a program. To be practical, the abstraction must discard information. For example, which calls correspond to which returns. The key is to discard as much information as possible for purposes of scalability, while still being able to prove the property of interest. An abstract interpretation is at the core of several industrial strength tools. Static analysis is gaining traction in practice with a variety of commercial products from a variety of companies, as well as open source tools. If you'd like to learn more about static analysis, I'd recommend this book, Secure Programming with Static Analysis by Brian Chess. This goes into more depth about how the static analysis tools work, elaborating on the description in this unit, and talks more about how static analysis fits in a secure development process. For more of the mathematical details of how program analysis works, I recommend this book by Nielsen, and Hankin. It's a bit dense for the casual reader, but it's good for introducing the academic field of static analysis.